Okay, good. Okay, yeah. So hi everyone. My name is Nikhil Barthwal. I'm giving this talk on implementing microservices as a serverless application. I believe microservices and serverless, they are both kind of really hot topic, right? Every second or third presentation in an architecture conference tend to be around microservices. But before I go into details on serverless, I first want to start with understanding the motivation of moving from monolithic to a microservice, right? So you have a monolithic application, the old school approach. Everything is simple, straightforward, easy to deploy, test. We all know that. The problem we run into is it doesn't scale, right? Why it doesn't scale? Well, you have a large code base, so it's slow development, more time to test, deploy, the teams, too much of interdependencies between teams, and so on. So we move to the microservices, the brave new world. Microservices is just a very simple concept, developing application rather than having one big service. You have a division of labor, right? So you have small services, the code generally tends to be stateless, and it could have like its own private database attached, and it communicates with lightweight mechanism. I guess there are many ways of communicating. You could use shared memory and all those, but that's typically the most common is communication using lightweight mechanism. And typically you have thousands of production. I was talking to somebody in Uber. He said he has 7,000 microservices running in production approximately, and that was like a year back. So I don't actually know what the number is now. So microservices gives us several advantages, right? To start with, we can release these services independently, so we have better scalability, better resource utilization. We can, we have a technology heterogeneity. We can just use different set of technologies. So everything's good. There's a lot of resilience built into the system. If one service fails, then it doesn't matter. The whole system might still work. There's just one service that goes down. And obviously, one big, very important aspect is ease of migration, right? Change is the only constant in this world. You would, at some point of time, migrate your system. So it's hard to do it. Like if you have one service, it's hard to migrate. If you have small services, it's easy to do it bit by bit. You have fast testing and deployment. So there's a lot of good stuff. But with good stuff comes the bad stuff, right? So what's the bad stuff? Well, we now have more moving parts in the system. And we know more moving parts means more complexity, right? We need more there's a need for automation. We talk about DevOps, we talk about all these automated testing. Well, in a monolithic, you actually can somehow manage things, in more like a manual manner. When you have like 7,000 services, you need a great deal of automation. You obviously have a complex deployment problem. Complex deployment because rather than deploying everything in once, you now have a concept of partial deployment, right? You have one set of services running in production with one version. They have they expect a contract between the services. Now you have changed, especially if you have changed the contract between services, it can get really nasty. And obviously, testing can become cumbersome. So what we have really here is we have traded one set of problem for another set of problem. The problem we were trying to solve is we couldn't really scale, we couldn't innovate faster. Well, with microservices, we can. But we also have to understand that with faster innovations comes more complex, a need for automation. There's a whole lot of problems that come with microservices. I call these problems, like, it's a common term to be used, undifferentiated heavy lifting, right? You have to handle all of these. And now, let's actually move to serverless computing and see how a lot of these problems can actually be solved using serverless computing. So let's actually start with the textbook definition of serverless computing. It's pretty simple. You have these various functions that communicate with each other, often in an synchronous. They run like an event-triggered component. They just respond to an event, right? The asynchronous mechanism. And you have a whole bunch of offerings by cloud provider. There's Lambda, there's Azure Functions, Google Cloud Functions, the three most common one. And what application model, basically the serverless application model does to you is it It consists of these independent functions that they interoperate, they have input-output bindings, and when an event happens, when something changes on the input, they react and they trigger another event, and one function may call another function. Typically, there are resource limits on each function. I think it's like 5 minutes or 7 minutes on AWS Lambda and Azure Function. There's also a limit on how much memory can use, but essentially the key idea of these functions are they tend to be really small. You can do a lot of heavy work in one function. Generally, no, there are workarounds for that, but that's not what they are designed for. And obviously, they communicate with each other. So it's an execution, asynchronous execution. You typically have a service bus, or you can just call these functions with each other. There's a common term that we have, which is FAS, functions as a service. So let's actually get back to microservices and serverless, and let's actually do a little bit of comparison here, right? So in the microservice world, we have an assembly of fine-grained services. Good. In serverless, we kind of do the same thing. We have the logic distributed in stateless containers, these event-triggered containers. What is common between both microservice and serverless is that both consist of applications that are composed of loosely coupled components, right? Loosely coupled in the sense that they are independent, basically, components. They just communicate through a contract, right? One doesn't affect the another one. So obviously, we understand that when you have an application that is loosely coupled, it has a lot of advantages to that. We would get to that. But the point I'm trying to make is we can implement microservices as a serverless functions. But the first question is, why would we do that? Well, when you observe the microservice monolithic kind of story, what you observe is, this is more of a problem with microservice, not so much about monolithic, right? You have one machine with a whole lot of stack. You have an OS, runtime, dependencies, applications. You have several sub-services, several instances. There is an auto-scaling required, and obviously there's a load balancer. Any cloud vendor that you use would provide you with all these components, but what they don't do, and what you have to do is you have to hook up these components yourself, right? So you have these components, you have a load balancer, ELB, you have mechanisms to auto-scale, but these are all the stuff that you actually have to do, right? So typically there's load balancing, there's scaling, there's service discovery, and all that means there's more management overhead. When you use, especially microservices, monolithic, not so much. Whereas, when you actually move to a serverless application, what you observe is a lot of it actually goes away. So your servers are abstracted. Obviously, there's a common misconception that serverless computing means I don't have servers. Well, you do have servers. You just don't have to manage them. They are abstracted out for you, right? It's an event-driven. There's an auto-scaling built in. And most important, sub-second billing, right? So you only pay for what you use. So what serverless brings to the table is less management overhead. So what we observed was, from monolithic to microservice, I increase my speed of innovation, but I bring in a lot of management overhead. And then when I move from microservice to serverless, I retain my speed of innovation. That doesn't get compromised, but I reduce a lot of the management overhead that comes with microservices when I move to serverless. So that's a huge gain that I have. But we know that we don't live in an ideal world, right? So for every advantage that we obviously would have certain disadvantages. And turns out, when you implement microservices as serverless applications, there are disadvantages also. So we'll get to what those disadvantages are and how to mitigate them. But let's take a step back. What are we talking about? Are we talking about something like we have to make a choice between serverless and microservices when you implement a system? More often than not, this is usually not the case. The real scenario is that most of the systems tend to be hybrid. So I would have part of my system in microservices, and I would have part of my system operating as serverless applications, and they kind of coexist, and they are part of the larger ecosystem. Why? Well, serverless has its own lot of disadvantages, right? It has benefits. I mean, it has benefits like it's cheaper to operate, and I know it's less management overhead, but I also know that there are disadvantages. I only have asynchronous method of communication. What if I want to communicate between two services synchronously? I can't do that, right? I also understand that there are resource limitations each function has. So what if I want to do something heavy and I don't want to, I don't want to have these limitations. In certain cases you could, in certain cases you can't. Microsoft Azure, for example, they have a very mature serverless offering, Azure Functions. So they have basically Azure App Service. I'm forgetting the name, but they do have a mechanism where they get rid of this resource limitation for you. But then obviously if you have something like that, it's not that cheaper to operate, right? But nevertheless, the point is, serverless has all its own drawbacks, right? In certain cases, you need it. On the other hand, microservices obviously have a benefit. They're always on. Well, one of the problems with serverless is these functions suffer from what is called as a cold start problem. What is a cold start problem? Well, the whole idea of serverless is that you pay for what you use, right? When you get an event, the function is triggered, but if the function is not really in a hot mode or it's not ready, the system basically has to orchestrate a new function for you. It has to deploy. All those things happen automatically behind the scene, but it has to basically boot up that function, right? So there's a latency involved with it, and that latency is called cold start, right? I'm not doing a hot start, I'm doing a cold start because the system boots up. So that introduces a delay. Well, with microservice, once you're deployed, it's always running. I mean, it's obviously the part is if it's always running, it's always consuming resources, so that is why it's not as cheap to operate as a serverless. But the fact is, it's always on. You don't really have any cold start problem. You also don't have any resource limitation. But when we know that it's always on, you're consuming more resources, hence it's a little bit more expensive to operate. So far, so good, and we just saw that there is a lot of management overhead with it. So what are the kind of services that makes more sense for serverless, and what are the things that makes more sense for microservices? So let's actually look at some communication patterns that we have. I like to divide the system in 3 tiers, right? So I'd say tier 1 is something that it's a customer facing, right? Tier 2 is something that impacts the customer indirectly, and tier 3 will be little to no impact to customers in the system. And you can basically divide your services in one of the 3 buckets. For example, let's say you're running an e-business, right? Your UI and your front end is a customer facing. If that goes down, basically your site is not usable, right? So that's a tier 1 service. Imagine something like order processing, right? You place an order, and the UI or the front end receives that order and puts it to another service that handles that order. If that service goes down, the customer doesn't really notice it. I mean, the only thing is there is a delay in the system. So let's say I place an order and I expect the order to be delivered in a couple of hours. If the service was down for half an hour, well, I can still place an order. My order would be delayed by half an hour. So it does impact me, but it's not a direct impact to me. And then, there are this third kind of service, for example, logging, monitoring, and so on, which is helpful to give you all the details of what's happening in the system, but the customer doesn't care. Turns out that most of the direct customer facing tends to be request response, right? Because I send a request, I get back, it's synchronous. And for such kind of services, microservice generally tends to be a better choice. Whereas when you look at tier 2 and tier 3, generally they would be event driven and they would be asynchronous in nature. So at that point, serverless tends to be a better choice. Now, one of the big advantages of synchronous is that you have a better error control. In the sense, if the service is down, I send a request, I get back a response, something is wrong, I know it immediately, right? For tier 1, you need error control because this impacts the customer directly. You can't afford the service to be down. Whereas for tier 2 and tier 3, what happens is when you're communicating asynchronously, a tier 2 service communicates to another tier 2 or tier 3, it sends a message through a message bus or whatever. It kind of goes in the ether. If the other service is down, I don't know that. Not directly, at least. I mean, I could have other mechanisms of figuring out. So error control usually is not that great in event-driven, but then since it doesn't impact the customer directly, it doesn't really matter that much. So coming back to the idea of distributed functionality, right? What happens is when you have more loosely coupled execution units, then it means that it reduces the team interdependencies. And the reason why it is because if I have to, let's say I am depending on a service A depends on team A depends on team B, maybe a good example. And if I have to deploy as a team A new service and I'm so much dependent on team B, then I have to synchronize with them, right? So, and imagine if this scenario you have like 100 teams, they're all interdependent. You have a lot of dependency on other team. You have to synchronize your deployment with them. They have to be on board, and sort of it limits yourself, your ability to, deploy, your ability to bring new features to market faster. So when you have loosely coupled components that agreed upon certain contracts, right? As long as you don't change the contract, you're kind of independent. There are times where contracts need to be changed, and in which case I do introduce team dependency, but the idea is that it's a small fraction of it. In most cases, my contracts tend to be the same. And what reduced team interdependency means is faster innovation to the market. So what we observe typically is we have this trend going on towards distributed functionality. We started with the monolithic system. Then since the last couple of years, we are talking about microservices. And when we look at serverless function, it's basically a natural extension of this idea of distributing the functionality, right? So when you think about your resources in the cloud, right? And you think about the whole concept of infrastructure to platform to function as a service, what you're really doing is you're offloading the stuff that you have to manage to the cloud, which is good. Good in the sense that you have less infrastructure to worry about, so you can focus your resources on your business. Obviously, there's a drawback. When I'm giving the control to someone else, I lose that control. So there is less control. In most cases, that is not a problem. So now that we have talked about microservices and serverless, let's actually look at some of the patterns and anti-patterns that we come across and how we need to resolve them. So one of the very common pattern that I have is a common data ownership, right? What is a common data ownership? Well, you use backend as a service, right? So there are these different, and I'm using the general term backend as a service. I'm a little bit cloud agnostic. I'm not talking about, it doesn't matter whether you're on Google and use Spanner or Azure as Cosmos DB, you have these backend as a service, right? And then you have all of these functions. So all of these functions, they access the data. When they access the data, what you have is, what you should not have is situation like this. And the reason why you should not have situation like this is because when you actually change the schema, what you observe is unexpected parts of the system breaks, right? Because you have too much of dependency here. If I change the schema of the middle one, it's a hodgepodge on how these functions would actually be changed. This is, in the microservice world, you also have a similar concept. What in the microservice world, it's an anti-pattern that if you share one database across two services or across multiple services, you shouldn't do that because that creates a dependency, and that kind of, it's basically lets you create team dependency, and it doesn't really give you the advantage of moving to microservice. I mean, the reason why you wanted to move to microservice in the first place was because you have independence and faster ability to innovate. You have just defeated your goal. So when you do something like that, you get what I call as the worst of both worlds, right? You have created a headache for yourself in terms of your nice little monolithic. Now you have these functions, but you also have all of these dependencies that you have cared about. So this makes the system very fragile. You never want to do that. What you want to aim for is something like schema isolation across teams. So how do you handle such scenario? Well, if you have backend as a service, right? We talked about this. What you want to do is, if there's a team A that owns a set of functions, I want to access this table. And similarly, if I have a team B that accesses it, well, then I have another set of functions, and so on. So this makes a lot more sense. There's a common question that arises: is how do I know, how do I know which function belongs to which team? And there's no hard and fast answer to that. It's actually a little bit of a problem specific. Usually something like domain-driven design can help you a lot. I know there was a talk on domain-driven design. I think in the morning Chris mentioned that, maybe not on public. Okay. Anyway, so you can use domain-driven design principles to divide up. There's a concept in domain-driven design called aggregate, which actually gives you a natural scene to partition your data. Domain-driven design is a big topic, and I obviously don't want to introduce it here for the lack of time. But I do want to talk about one caution that you have to exercise. When you're talking about a scenario like this, where you have one table and you have functions that are basically accessing, this kind of becomes your deployment unit or a deployment group. Because if you do something like a schema change, what that means is you have to deploy this entire group. So essentially, the way you want to think about it is that I have replaced this one service with a set of functions. And this set of functions is basically one unit, right? When I'm deploying it, I'm deploying this one unit. In microservice or service world, because there are no constraints on the amount of resources I can consume, I can replace all of these functions by one service. But in a serverless world, I can't do that because I have constraints. So I have to divide my functionality into functions, which is okay, which is not a problem. But I have to understand that I'm creating a grouping here, a grouping of deployment. So talking about functionality, we have to talk about fine-grained functionality. Now, one of the common things that I've observed is people talk about serverless function, they design a system, then they implement it, all those things. But really, to me, design is like an ongoing process, right? We have talked about agile. It's something that you do continuous, because what you have is you have this function that is implemented, right? And you keep adding and adding this functionality. So you go into the small function, the little green dot expands to a big green dot, and then what you realize is it's too big for you to handle. So what you do is you do a split. And this process is continuous, and you need that because functions have resource limits. So one of the pattern that you want to do here is you want to distribute your functionality in small chunks, right, as small as possible. So design kind of becomes it's a continuous. You need to continuously refactor, right? It's a continuous process here that we are talking about. Another problem that we have here is, and this is more of a problem in hybrid systems, is that imagine you have a database. Now you would not have a database if you're designing a system, if a serverless system from ground up, but this is more of a common scenario when you're migrating your on-premise application to the cloud. You still have some databases, you haven't replaced it with backend as a service, and then you have all these functions that are running, as these functions are auto-scaled. When they are auto-scaled, right, you have no control over how the scaling happens, and what happens is it increases the pressure on the database because you have too many connections, right? The load increases, the auto-scale instances goes to, I don't know, 10,000, you have 10,000 connections to the database, and the next thing you observe is burnout, right? So that's a concern, and there are ways in which you want to address those concerns. So one common way is to prevent burnout, I would use a circuit breaker, right? Concept of circuit breaker exists in microservices also. Concept of circuit breakers is actually pretty common. It probably exists in this room also. You have a circuit breaker. When the load increases above a certain threshold, what you do is you chop off, you break the connection. So that's circuit breaker. You obviously have connection pooling, right? You can pool the connections, but the easiest and probably the best way to prevent such a problem is use backend as a service, because when you use backend as a service, all of these problems get offloaded to cloud vendor who has already thought of and implemented a lot of these solutions. So this probably would work best if you could do it. Generally, a pattern of using database, like I mentioned, isn't really a good one. It occurs when you're migrating from one architecture to serverless pattern. So let's go into something like CAP theorem, eventual consistency, right? So we have three different concepts. In a cloud where you're operating in different zone, we obviously have a problem. We have systems that are there in data that is spread across different locations, across different data centers. So you need consistency. You obviously want availability, and you want network partition tolerant. Now, if you have a distributed system, the third one is a must. Availability becomes very high because in these systems that are highly available, downtime costs you a lot. Imagine every minute that some website like Amazon.com is down. I don't have the numbers, but I'm going to guess that every minute will cost them probably a few millions, maybe. I don't know. But we know that we can't have all three. So what we do is we have to sacrifice one. And the one we sacrifice is consistency. So we go into what is called as eventual consistency, right? And eventual consistency means that when I do an operation, my data would not be consistent at that point of time, but the way I've designed that system, eventually it would get consistent. And this eventually is quote unquote eventually. It eventually could actually be a couple of seconds or couple of minutes. Usually it would not matter, because imagine if you're using Amazon, right, and you place an order sitting in New York, and the data is getting replicated in California. So somebody who logs into your account in California will not see that order immediately. It might take like 1 minute for him to see, but what difference would it make? And this gives rise to what we call as event-driven architecture. It's actually, event-driven architecture is like a buzzword you hear quite a lot. And what event-driven architecture basically does for you is it gives you a way to solve a problem. And we'll see more examples, but basically design a system which is eventually consistent, available, yet network partition. Now, this is not the only way of doing it. There are other ways of doing it. This is the most popular way of doing it. And it's so much so that event-driven microservices, people just take microservices and event-driven microservices as the same thing. They are not the same thing. Microservices is a general term. Event-driven microservice is a subset that basically uses this eventual consistency while giving you availability in partition. There are other ways of doing it. So the question is, how do you get into this scenario? How do I have eventual consistency? The problems with most of these distributed systems is that you have a concept of partial failure. So to solve that problem, we introduce Sagas, right? The original concept of Saga was actually, it came up somewhere in 1987 or something, if I'm correct. And it emerged in the way of databases. But they had to be modified a lot, because in databases back in at least 1987, you didn't really have distributed systems, so there was no such concept of partial failure. So what Sagas is basically, it's a long-running transactions. And what Sagas do have is they have compensating actions to handle such failures. So I'll start with an example of what it is. Imagine if I take a money from one of you, right? So I deposit a check. This initiates a Saga, right? So this initiates a Saga. I go to the account, I deposit check. So you have a service, a function, whatever, sender has enough money, it checks, It goes, it withdraws. If it's not, it goes back. Everything is great. Deposit, and once it has, there are a sequence of actions and they are communicating via events. In this case, everything is good, but what you also need is you need a compensating actions to handle failures. For example, so what we have is we have transactions, right? And we have rollback transactions. So every successful operation or every transaction has a rollback transaction associated with it. And this logic must be included in the service. So let's actually look at an example of how it would happen. So you have a transaction, okay? You have a transaction, it happens, and let's say you have a T2 operation. T2 operation in an ideal world should talk to T3, which is another transaction. But what happened was, this happened. So when this happened, what do? You actually go back. You can't do this because this transaction failed. So what you do is you go to rollback. So so basically what you have is you have a series of transactions and you have a series of rollback. For example, and this actually can get quite complicated. So let's actually look at the previous example. I get a check. I have first transaction that says, do I have enough money? I give a check to somebody and I say, do I have enough money in my account? Sure, good. The check goes to the other person, and before the money gets deposited, does he have an account? What if he closes an account? What if I give a check to somebody and he goes, that check basically by the time it's in cash, the account is closed. So you would go back and you would check for a transaction, the account is valid still, so I can put money. If not, you go for a rollback transaction in the sense the check would bounce. This is not a valid account. Now, simple example, but what happens is just before the check bounces, I close my account. So I have this money which is floating everywhere and it nowhere knows because the account from which it was drawn doesn't exist and the account to which it was supposed to go doesn't exist. So the scenario of transaction and rollback transaction, when you do it at a large scale, it can get a little bit complicated. Anyhow, so we have another concern, big concern with serverless application, and that is vendor lock-in. And the reason why we have this concern is because serverless is relatively a new offering. So it's not functionally equivalent across vendors. Some vendors, they give you a really good ability. For example, I'd say among all the offerings, Microsoft Azure probably has the best serverless offering, right? I can run my functions locally, I can have local execution, I can run them remotely, I can even debug them remotely, and they give you a wide variety of technology choices. Amazon also gives them, but Amazon has a limitation. I mean, you can't really, the last I checked, you can't really run Lambda functions locally. There is a framework which is an open source framework, not officially from Amazon, that lets you do it, but Amazon itself does not have anything like that. Google function, and I have to admit I checked Google functions as back as early this year, so probably things have changed, but at the time when I checked, which was February, the only language they support is basically Node.js. You can't really have any other language to use functions. I think that has changed now. They probably support a lot more tools and frameworks and languages, but at that time they weren't. The point being that serverless is still an emerging technology, and it's not really standard. It has a lot of benefits, but it comes with a drawback, and that is higher cost of migration. In future, when you use a serverless on a platform, you can get into vendor lock-in. Now, a common trade-off that people tend to use is to use an abstraction layer, and there are limitations with an abstraction layer. The limitation with an abstraction layer is when I have abstracted out, let's say I have some intermediate framework or layer that kind of abstracts out all the major cloud vendors, what I get is the lowest common denominator of the three, right? Because there might be certain features that Azure Functions has that AWS Lambda does not. And if I get a lowest common denominator, there are a lot of good stuff that I'm actually leaving on the table I can't use because I have to be compatible. So this is a drawback, and it's not always a solution. There are times where it makes sense, but there are times it doesn't. There's usually no particular way to get out of this situation as of now, but like everything in engineering kind of becomes a trade-off. So when you basically get into a serverless implementation, it's like this: you get a lot of good stuff, but you have to suffer from a drawback. It's a technical debt that you're probably creating right now for future. The good thing or the bad thing about future is you can't really see what's happening in future. So you just have to live with it, that someday maybe I have to move across vendor, and if this particular feature is not available, I would get into a problem and I would have to re-implement certain parts of my system. Another concern is security. So we have this OS kernel, it's shared across containers, all good. And then you have this container OS, and then you have the functions. The problem is it's still sharing the same kernel, which means it is theoretically possible for one function to access data on another function. Now, I chose the word theoretically because in practical scenarios, the probability that such a thing would happen is actually not that much. And the reason why it isn't that big of a concern is, to start with, vendor gives you an isolation, right? So you have an isolation built in. Secondly, you have to understand that these functions are generally short-lived, right? They don't really stay there for that long. So you really, if you want to access somebody's data, you have to really move very quickly. And to make the problems worse, you don't know which function is running. I mean, I know that I'm sharing an OS kernel with someone. I just don't know who that person is, right? Scheduling is very independent. The vendor is giving you a scheduling. I have no control over it. So it's not usually that much of a problem, but I do have to understand that I'm sharing my kernel with someone else. So far, so good. On a small scale, everything works. But what about large scale projects? I mean, now we are talking about replacing big monolithics with microservices and serverless. What are the things that I have to keep in mind? To start with, versioning can be very difficult, because remember that you are now functions are communicating with each other in an asynchronous manner. And the problem with asynchronous manner is something fails, I generally would not know. In a synchronous manner, or let's say if I'm in a monolithic application, if I have an exception, there's an exception stack that tells me where it originated and how it propagated. When you have asynchronous communication mechanism, if something fails, I don't know what originated. So because the system is generally a little more fragile and my data contracts can change, versioning can be very difficult, right? So it's important for me to ensure that consistency of contracts across function is needed. It's kind of difficult. One solution is a monorepo, right? You have all your code in one repo. This is kind of a debatable topic. Some people are fan of monorepo, a lot of people are not, and I don't want to go into the debate by itself. There are practical implementations. For example, Microsoft provides you, I think, Git VFS, which is kind of a monorepo, and I think Facebook has worked on some open source implementations. But I just want to end with a caution that monorepo can be pretty difficult to implement. So that's something you want to keep in mind. Another caution is that testing the functions can be really hard. And there are ways to mitigate it. For the first one is use local execution whenever it's possible. Like I mentioned, Azure Functions gives you the ability to execute locally. In fact, Azure Functions also give you to operate in a hybrid environment where you have part of the system running in cloud and part of the system running on your local premise, and pretty much interact with each other seamlessly. Amazon does not really have such ability directly, but there are tools and frameworks that let you kind of mitigate it. To the best of my knowledge, Google Cloud Function does not give you any local execution ability. Again, there might be something, but at least I'm not aware of it. Second, remote debugging. Like again, for certain vendors like Azure Functions, you actually can attach a process to a function running in the cloud and remote debug. But your easiest and the best way is you have logs coming out, right? So you can monitor the logs. Logging is built in on these platforms. The only problem with logs is that usually you have to aggregate the logs somewhere. There are platforms like Splunk that would basically let you do that. So you can have like a request ID, and then you can aggregate logs on how that request is basically going through these functions and somehow aggregate and see what's happening overall. You obviously have ways of testing a function using kernel and command lines. You can have other functions like write functions to test other functions, but generally, testing functions is generally hard. So that's a drawback of serverless application. Speaking on which, I'll extend it. What happens is that when you have like a, functions, you have this ability to, I have to write a function, I develop it, then I deploy it, then I test it. So the feedback cycle is a lot more longer, right? Because I actually have to deploy my code to the cloud to get the feedback cycle. But when I have something like local execution, I can actually get a lot quicker feedback. Another aspect of it is, now we have talked about serverless, I want to touch a little bit on, I have a system, let's say I have a system, Monolith or Microservices. I want to move to a serverless platform. I know there are a lot of advantages on it. What should be my strategy for migrating my services to serverless? And what everybody understands from their experience pretty much mostly is that integration is not an easy thing. It's pretty hard. So how you start about with such a migration is, the first thing you do is you want to decouple your components, right? Because remember, you have to divide your functionality across these functions. So decouple your components, and typically the first step of migration is migrate your data to a backend as a service first, right? Because every app needs a data, and when you have a data, you can just slowly and slowly migrate the functionality. An easy target for migration generally tends to be message queues. And then finally, in some cases, you can just lift and shift the code, right? Take it and just apply it as a function, but it's easier said than done because, like I said, functions have resource limits, so you might have to modify, you might have to split. It can get tricky. But the point is that integrations can actually be challenged, so it's actually a little bit of a challenge for you to migrate to serverless if you already have an existing system. It's usually easy to develop new functionalities in a serverless architecture and have them interact with what you already have running. Towards the end, I would touch upon some of the advantages of serverless implementation of microservices. The first big one is that when I move to serverless, right, a lot of things I'm getting out of the box. For example, auto-scaling, monitoring, logging, a lot of it. So I can really focus on my application code and let all the runtime and OS and everything be managed by the vendor. So I have out-of-box scaling, I have load balancing, I just have everything. And it's a lot more cheaper. Why? Because it's a pay-as-you-go model. I have a sub-second billing. I only pay for what I use. That's a big advantage, cheaper to operate. There are obviously some disadvantages also. If you just stick with the serverless domain, then one big disadvantage is I only have asynchronous method of communication available, just within the serverless, of course. Like I mentioned, in real world, you probably won't do that. You would have microservices and serverless running side by side, so that is not a disadvantage in a hybrid system, but within a serverless domain, you have this problem. You also have a problem of cold start. So I mentioned it before, if your function, because your function is auto-provisioned, if you're not using that function, it gets deprovisioned, and if you then suddenly make a call, the first time the function has to boot up, it takes a lot of time. So you have a cold start problem. Another issue is you have vendor lock-in, right? Because serverless is relatively a new technology, so it's not really very standard across different vendors. I think this problem is probably going to be gone, but it might still take some time. There were some frameworks actually. One of them is called Serverless Framework. The name is Serverless Framework. I don't exactly know the URL, but if you search on the web, I'm pretty sure you'd hit the URL. And what the Serverless Framework basically is doing is it's essentially abstracting out different vendors. But then we know that when we do that, we kind of get the lowest common denominator. So how useful is it in the practice as of now? I'm a little doubtful. I hope the situation would change in future, but as of now, I have my doubts on that. Towards the end, I just want to summarize some of the things that I touched upon, and that is implementing microservices as a serverless function has big benefits. Microsoft tends to have a lot, microservices tend to have a higher management overhead that I know that when I migrate to serverless, I would actually mitigate a lot of these problems. But in most cases, real-life systems tend to be hybrid. Thank you, and I have 5 minutes and 1 second exactly remaining, so I can take questions. Yes, sir.
So, when you're talking about only asynchronous execution, there are problems in
Can you speak a little loudly, please?
Yeah.
Is there a microphone we can get?
fine.
Okay.
I can speak louder. So you can plug like API gateways to go online or like synchronous execution
Yeah.
rather than asynchronous. Those fall into this category of serverless?
Well, you could do that, but if you add all those stuff, you have to maintain them, right? So the very reason why you moved into serverless was because you want less maintenance to do. If I add all of these, then I've defeated the purpose of moving. I don't use a technology just for the sake of using a technology. I use a technology to solve a problem. I haven't really solved that problem. But again, it's a very general question, so the answer is it depends. Because depending on system to system, I have to understand that how much more overhead I'm creating for myself. If there's a benefit and I'm not creating any significant overhead, sure, why not? Particularly if you have an existing API gateway or something running, you might be able to migrate it as it is to a serverless. More questions? Yes?
We got Service Fabric in Azure.
Sorry?
Service Fabric in Azure. Would you consider it as a serverless or not?
I am not particularly aware of serverless, but I don't think Service Fabric would be considered as a serverless. I mean, serverless has some distinct characteristic. It's more of a PaaS, basically, if I'm correct, right?
Yeah.
So it's more of a platform in the service in the sense that you have an abstraction of server done for you, but serverless has certain distinct characteristics like these small these small functions that communicate. And something like a PaaS doesn't really fall into that. So I wouldn't exactly consider it as serverless. But what I'm wondering is, why is this question important? In the sense that I have a set of specific problems that I'm trying to solve with whatever technology, right? And like I know every technology, every decision I make has trade-offs. So if Service Fabric solves some of the problems that I have without creating any more problems for me, I would move there. Whether it's a serverless or not, why should I care? I'm looking more not from the use of technology point of view as much as what is it that it can do for me, right? So it's a wrong way of thinking of, is this serverless, so I'm going to use it. If it's not, I'm not going to use it. That's not how you really use technology, right? More questions? Any? Yes, sir.
Can you name few real products that uses serverless or at least combination?
The thing is that can I name? I mean, I can. The question is, should I? I am bound by my proprietary, But I mean, I can tell you, Jet.com uses it in real life, definitely. Most of the technology, I mean, some they publish their architecture details. A lot of them don't. So I would assume a lot of them would use it. The question is, do they publish it online? Maybe not. I did had a talk with a manager in Google, and she was telling me that a lot of, without naming the actual products or the companies, she did said that they have a lot of hybrid scenario that they use. So it's definitely it's something very real that people use. Questions? More questions, if any? I don't know how much time I have left. Yes, sir.
What kind of backend as a service that you experience with?
I have mostly used Azure Cosmos DB and Azure Table Storage. Azure used to have an Azure Blob Storage. It's still there, I think, but nobody tends to use it because Cosmos DB has kind of replaced it. Google Cloud has excellent BaaS service. I think Google Spanner and Bigtable. I'm not that familiar with Google Cloud as of now. And obviously, we have DynamoDB on the AWS. Like serverless, BaaS is not something that's more vendor specific. So your vendor would have something, but depending on what vendor you use, that I'm not aware of. Any more questions? Yes, sir.
Yes, I read on some of these websites that they are not providing 100% uptime.
Yeah.
Just 99.
Yeah.
Or something. So how you handle that situation when actually something is done?
So the thing is, you can't really so much as handle it, in the sense you have to put stuff that don't need 100% uptime into serverless, into functions. If it needs 100% uptime, you probably shouldn't be using function in that case first way. And this is where the hybrid scenario comes in, right? Microservices is something that is 100% uptime. So put the functionality that you absolutely need available in the microservice, and put the functionality that you can tolerate occasional non-availability in the function, because you have a cold start problem there anyway. Any more questions? Thank you.